Welcome back to Physics 152 Online. We have already discussed the wave properties of light, and now we're actually going to go backwards in time and look at the simple understanding of light, thinking of it as primarily a propagation of particles in a stream that we refer to as ray optics or geometric optics. And much of our everyday experience seems to indicate that this is the way that light actually behaves. If you see light streaming through some slits in the blinds on a sunny day and you're in a dark room, you'll sometimes be able to see beams or rays of light scattered from the dust that's in the air in the room. And so it really does appear to our everyday experience as if light interacts with lenses and mirrors and our eyes as if it's traveling in straight line paths. And so that generally holds true unless the light interacts with objects or apertures that are small compared to the wavelength of light. And so this limiting case of geometric optics works really well when the lenses or the mirrors or the holes that light passes through are large compared to the wavelength of light. So in general, let's first look at what happens when light in one transparent medium hits an interface with another transparent medium. The general case is that part of the light that comes in is transmitted through into the second medium and part is reflected. And let's look at the quantitative relationships relating the incident light path to the reflected or the transmitted light path. But first, some basic review of the fundamental properties of light. The speed of light in a vacuum, once scientists were able to measure that for the first time, was measured more and more carefully and settled on a value for light in a vacuum at a speed of approximately 3 times 10 to the 8th meters per second. Now in a transparent medium that is not a vacuum, that actually has some matter to it like glass or plastic, that velocity is actually decreased slightly according to a property of the medium that we call the index of refraction. So the true velocity in the medium is the speed of light in the vacuum divided by this number, the index of refraction, and you can see the value for some typical materials listed in the table. Also, something that's a little bit subtle but is an important property is that the index of refraction of a particular material is not just a property of that material, but it depends on the wavelength of the incident light. So you can see here that different kinds of glasses have indices of refraction that vary across the visible spectrum by several hundredths or tenths in the value of the index. And so that's important, as we'll see a little bit later, for the way that a prism acts on white light. First of all, though, if we look at the incident path of a ray of light traveling towards an interface between medium 1 and medium 2, as we said, part of that light will be reflected. That's the reflected ray path, and part of it will be refracted. And there was a simple property that was known to the ancient Greeks, which is that the reflected ray makes an angle with the normal direction to the surface that's the same as the incident angle. So in the relationships that we're going to write down, we will always measure the angle of the path away from the surface normal, or the dotted line here. So the Greeks knew that theta 1 prime was equal to theta 1 from simple experiments that they did. And they knew too that the light that traveled from one medium into a different medium was bent. But it wasn't discovered till later exactly what that quantitative relationship was. And although it was discovered by others earlier, the law that we write down to describe the relationship between the incident and the refracted or the bent ray is known as Snell's law. And Snell's law tells us, and we can verify this experimentally, that the product of the index of refraction and the sine of the angle is the same on both sides of the interface. So n2 times the sine of theta 2 is equal to n1 times the sine of theta 1. And you can see in this example here, we must have a situation where n2 is greater than n1 because theta 2 is less than theta 1. Snell discovered this law, and others before him discovered it just by doing experiments, but in the 17th century, the French mathematician Fermat gave a quantitative derivation of how you would actually predict this kind of relationship. Now, a consequence of this relation tells us the way that the light is bent. So if you have incoming light in one medium and you want to understand the path of the light that travels into the next medium, the transmitted or the refracted beam, Snell's law tells you that if you're going into a medium with a higher index, then the light is bent toward the surface normal, resulting in a smaller angle. Theta 2 then is less than theta 1 if n2 is greater than n1. And the same kind of thing happens in reverse. If the light were to come originally from inside the medium n2 and travel towards that interface, it would be bent away from the surface normal. So this path, if you just reverse the direction of the arrows, would also hold true in reverse. I mentioned just a minute ago that the index of refraction of light actually in a particular medium depends a little bit on the wavelength. And so the angles of refraction for red and for violet, the two extreme ends of the visible spectrum, are different. And this is why white light, when it encounters a surface with a medium like glass, actually separates out into different colors. We can see an example of that here. And Newton was the first one to demonstrate this and was able to make some of the first measurements, quantitative measurements, about the composition of white light. Now, a consequence of Snell's law is that something very interesting happens when light starts off. Let's say that there's a source down here at the bottom left of this diagram that sends light towards the interface, and here we have a situation where n1, the medium in which the light starts off, is greater than n2. So you can see that as theta 1 gets larger and larger, theta 2 gets larger and larger as well. And eventually we will get to an angle where, using Snell's law, theta 1 gets to a point where theta 2 has to reach 90 degrees, or pi over 2. And what happens at that point is the refracted beam disappears, because if you tried to solve for theta 2 beyond that point, you wouldn't get a real answer. So what happens in that case physically is, instead of some of the light being transmitted and some of the light being reflected, all of the light gets reflected. And you can see in these last two beams on the right hand side, all the light is reflected and none of it is transmitted into the medium n1. And this phenomenon is called total internal reflection. And for a simple example, we can calculate what that critical angle is that would cause all of the incident light to be reflected and not to be transmitted at all. So let's imagine that we have a light source where the beam of light is inside a piece of plastic and it has an index of refraction 1.5 and an incident angle theta 1. We just showed that if theta 1 gets larger and larger, eventually the angle in medium 2 will become 90. And if medium 2 is a vacuum, or if it's air, which has an index of refraction pretty close to that of vacuum, we can calculate the critical angle. So we take Snell's law, and then the second medium, which is medium 2 here, we set that angle equal to 90 and plug it into Snell's law, and so that would tell us that n1 times 1 is equal to n1 sine theta 1 c, and we'll label this angle theta 1 critical because it's just got a special value. And all we have to do now is solve for that angle using the two indices of refraction in the problem. So sine theta 1 critical is 1 over 1.5, and if we solve for the angle, it's 41.8 degrees. So what does that mean physically? It means if the angle theta 1 is less than 41.8, some of the light will get reflected and some of it will get transmitted. But when it equals 41.8 or is any greater than 41.8, all of the light will simply be reflected and none of it will be transmitted. Now here's a nice demonstration where we have a light shining into a partially filled aquarium from the top. So the incident beam is downward, as indicated here, and it hits the surface of the water, and then underwater there are three different mirrors. So the light hits all three mirrors and produces three different beams that make different incident angles with the water-air interface. And you can see that the first two beams have angles that are small enough where some of the light is refracted, transmitted into the air. But the last one on the right has an angle that's greater than the critical angle, and as a result, all of the light is reflected and none of it is transmitted. So that's a great illustration of this phenomenon of total internal reflection. And there's one more example of a more practical nature that I can tell you about, and that is in light wave communication using optical fibers. There are special materials that are transparent materials that we can make optical fibers out of that are flexible and can be bent, and if you shine light into them, the light will always hit the interface from the fiber to the air around it at an angle that's greater than the critical angle for total internal reflection. And so this is a great way to take a signal that's carried by a pulse of light and basically bend it around the corners of a fiber and have it travel very, very large distances. And this is what most landline type networks are now based on, carrying signals through optical fibers. And a lot of computer network signals are also carried this way. So it minimizes the need for re-amplification of the signal, even though eventually, with long distances, those signals do have to be detected and then re-amplified. But if you draw in the surface normal at each of the points here where the light hits the interface, you can see that it's always going to be greater than that value we calculated a minute ago, which is about 41.8 degrees. So there are practical ramifications of total internal reflection. And that's enough for now for our introduction. Next, we'll be moving into the discussion of how light is bent at a curved surface with a lens, and how it is that lenses cause light to be bent and focused, and we make use of those properties in all kinds of optical instruments. I'll see you in class.